components of the pyruvate dehydrogenase complex. Okay? Now, if we look at, right, so down here are the structures of these coenzymes. The thiamine pyrophosphate, right, that's here. It's this thiazolium ring, right, this sulfur-containing ring, that is the interesting part. Lipoamide is here, right? Lipoamide is a long-chain disulfide. The carbonyl of that long chain is linked via an amide linkage to a lysine in the enzyme. So you have a lysine, essentially a peptide bond, this long chain. This is the oxidized form of the lipoic acid, the lipoamide structure. So that's that one. FAD, I didn't show, right? Because we should know that one. NAD I didn't show. And this is our coenzyme A, right? So here's the adenosine, pyrophosphate, linking through a pantothenic acid. Pantothenic acid is one of our essential vitamins. And then the beta-mercaptoethylamine, which is derived by decarboxylating serine, and it's the sulfhydryl at the end, which is where the chemistry goes on in coenzyme A. Okay? So, orienting ourselves to the structures. No, I'm not going to ask you to draw these structures. So, yeah.
Okay, this whole time I've been confused. What is the relationship between E1, like the pyruvate dehydrogenase, and the thiamine pyrophosphate?
Well, they're part of. Right? They're part of this structure. So all three of those enzymes, right? These different colors are representing those different enzymes arranged so that they can interact with each other. So we've got three different enzyme activities all put together. Really what we're creating is an enzyme assembly line. Right? Three enzymes working together in a stepwise fashion to accomplish the conversion that we associate with the pyruvate dehydrogenase reaction. Does that make sense?
Well, yeah, so there's three enzymes, and then what is thiamine pyrophosphate? Is that?
Well, those are the coenzymes, right? Remember, that help the enzymes with its function. We'll show what each does in the mechanism. Okay? So, right, there's the size. There's another picture of a pyruvate dehydrogenase. Okay? Now, yeah, Robbie?
What's the advantage of having a complex instead of like a cascading pathway like also?
What I just said, which is that these three closely related reactions can directly interact in an assembly line. The products of one can be directly transferred to the next step without the time loss of diffusion and rebinding. Okay? Okay? Now, part of this we've done, because we talked about pyruvate decarboxylase. So the first step works like pyruvate decarboxylase that we talked about. The thiamine pyrophosphate of E1 is deprotonated to make a negative positive zwitterion. What do we call something that is a zwitterion with the negative charge and the positive charge on adjacent atoms? What is it? An ylid, right? So it creates an ylid. Right? Ylid being your good Scrabble word of the day. Right? If you play ylid, someone's going to challenge you.
They don't let you do chemistry words.
They won't let you do chemistry words. It's a word. Anyway, so that ylid acts as a nucleophile, attacks the carbonyl of pyruvate, creates a new carbon-nitrogen double bond that allows the decarboxylation reaction, right? Remember, the carbon-nitrogen double bond creates a new positioning for the bond that will break, and so we can decarboxylate. So you get the decarboxylated pyruvate, 2 carbons left, down to the ylid. And this is called the hydroxyethyl thiamine pyrophosphate form. Okay. So we decarboxylate, which is what we did before. Right? Now, so now we've decarboxylated. So now that step puts us here on this figure. So that's going on in E1. Now, the next step is, and I'm not going to worry about the mechanism here, this oxidized form of the lipoamide, right, this disulfide form in a 5-membered ring, accepts those carbons. I believe what happens is the negative charge here acts as a nucleophile on this sulfur. Sulfur is a good leaving group, so that opens the ring, and then that is protonated. And because we're adding 2 electrons to the system, that is reducing this, right? So if we count the electrons, this is reduced relative to this when we transfer that 2-carbon group. So we transfer that 2-carbon group, it ends up being an acetyl group. So our lipoamide ends up carrying the acetyl group. Yeah?
Is there a reason it attacks one of the sulfurs instead of the other one?
Why would we expect it would attack one instead of the other?
I was just going to ask if it's just the enzyme directs it.
Just the enzyme directs it, exactly. Now, the cool thing about the lipoamide, now if we go back to this picture that I had before, right? If we look at this, from the protein backbone to the sulfur where that acetyl group is attached is a chain of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 atoms. Right? That's a nice long chain. And so this is long, and what do we know about each of these bonds here, 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 here? What do we know about those? They can rotate. So this ends up being a long, flexible chain. And so really what this chain is doing, right, is in this process, right, go to here. Yeah, I don't care about that. Right. In this process, yeah, let's stay here, right? This chain has to reach over to the thiamine pyrophosphate and do the chemistry that transfers the 2-carbon group there. And then this chain, right, this long chain, is going to reach over to its own active site, where it's going to transfer this acetyl group to CoA. So this long floppy chain is really doing this, reaching over to the E1 active site, picking up an acetyl group, and then flopping over to the E2 active site to give that acetyl group to coenzyme A. And so that link is important because it's going back and forth as a carrier of that acetyl group. Does that make sense?
That's the lipoamide.
Yeah, that's that lipoamide, that long chain that we talked about, right? Because it's got to reach into the active site of E1 to pick up the acetyl group. And it's got to deliver it to the active site of E2 where it transfers that to coenzyme A. Right? Now, what kind of bond is this that we created when we did this?
Thioester.
Thioester. What do we know about thioesters? High energy. But if we use CoA and its thiol as a nucleophile to attack this ester, what kind of bond do we create? A thioester, right? So it's actually this transfer that creates the high energy bond. And so we trade one high energy bond for another one in the transfer to coenzyme A. Does that make sense? But we leave our lipoamide then in a reduced form. Now, as long as this is a thiol, we would expect, right, this to be reversible. Right? That could attack just as well as that could have, and that this step would be reversible. How do we keep this step from reversing? What do we have to do to go from here to here?
Oxidize it.
We have to oxidize it. So when we oxidize this, we take the thiol out of the system. And so that step then is no longer reversible. Right? We remove the product by oxidizing it. Does that make sense? So now we need to talk about how we oxidize it. Right? So oxidizing it is the role of E3. Right? E3 has FAD as part of its tertiary structure. It also has two cysteines that normally create a disulfide. Right? So these are the sulfurs of two cysteine amino acids in E3 that are creating their own disulfide linkage.
Step 2 and 3, both in E2 or 1 and 2?
Well, step 2 is occurring when the lipoamide is reaching over into the active site of E1 to pick up the acetyl group. Step 3 is occurring in the active site of E2. Okay? Where's step 4 going to be?
In E3. Wait.
Where's step 4 going to be?
It's still the lipo.
It's still the lipoamide. We got awfully quiet. Well, it's the active site of E3. So this is the third place that lipoamide has to reach. Right? Now the lipoamide has to reach into the active site of E3 so that it can be oxidized properly so that we can continue the process. So this is the third place that floppy lipoamide has to reach. And so now are you starting to see why putting these things together in a complex is much more efficient, right? Because this one coenzyme of E2 has to interact with all three proteins. It has to interact with itself, has to interact with E1, and it has to interact with E3.